Hi, this is recording for summary of lectures 3 and 4 from week 2. Okay, so we are talking about linear models. So this is where in an example of, so the main topics that are covered are input representation, classification, regression, and nonlinear transformation. In terms of input representation, the problem is of detecting digits which are used for, sorting postal codes. And the idea is that this is a 256 by 256 bit pixel image of just whites and blacks, that is zeros and ones. So in an ideal case, that may be 256 by 256. So there's a 256 by 256 matrix. And how can you reduce this? So what we can do is extract two features. One is intensity and summary symmetry. Intensity is the intensity of the black dots. You can imagine that 8 will have a higher intensity than 1, and so is symmetry, that 8 will be more symmetric than, let's say, a 5. So you can transform the original input vector x0, which is the constant weight, x1 to x256, by just x0, x1, and x2, and the weights will be just w0, w1, and w2. The idea is that you are greatly reducing the input space of the dimensionality of the input space, and we'll see later why this is important. And gives you some idea of, you can actually do something good if you look at 1s and 5s. And if you plot intensity by symmetry, you can see that 5 is more asymmetrical than 1, but 5 is definitely more intense than 1. Okay, and now what you will see is what the perceptron learning algorithm, what it does is it fluctuates. So it will fluctuate, it will move the gradient, the separating line across all these points, and it will iterate over all the points. So you can imagine that it just depends where it ends, and that will be kind of the E in. And right now this is just for illustrative purposes, that the E out is also plotted. E out you don't really know because that's the out of sample error. But the important thing to note is that if you had stopped E in, at one of these points, it would have been very low, but now it's kind of very high because you just stopped at a different point. And the idea is, having a pocket algorithm, what that means is just remember the last good known E in and kind of keep that. And only if we see an E in that is better than this, can you take that. Otherwise, just use this particular E in. So you can see that this is the difference. The perceptron learning algorithm, the separation is here, and for the pocket, the separation is here, which is much better. Now look at regression. So so this was classification. We spoke about the dimensionality reduction. Now what about input regression? Regression is the only idea is it's a real valued output, and it's called regression for historical reasons, that it's kept it that way. And the idea here is, instead of just a classification between true false, you give it a specific number, and you can imagine that you have to define what is the credit approve. Instead of just the credit approval, you have to actually give a credit value, that I can give this loan of so many dollars to this particular person. And this is the regression output. And okay, so it's something similar. Now how to measure the error? Let's say this is the hypothesis function and this is the actual function. You can imagine in linear regression we use squared error. We'll see that why are we using squared error? We are assuming a Gaussian or a normal distribution, and the sample error is just an average of that. And this is an example of multiple dimensions. This is just across one dimension, across two dimensions. So basically it's an hyperplane, and here's where we are expressing this as matrix notation. And what we are currently doing is we are trying to write En as matrix. And you can see where X is this particular matrix of x1 transpose x2 transpose y is this, and minimizing EIN is you take a derivative and you come up with the pseudo inverse of x, and we'll talk about the pseudo inverse. And this is the pseudo inverse. It is x transpose x inverse, and here's where you will see x transpose x is just dn plus 1 cross dn plus 1. This is the dimensionality of this matrix, and it is much easier to, let's say, inverse a 3 by 3 or 4 by 4 matrix than a 200 by a 256 by 256 matrix. It can still be done, but this is just an easier operation. And the idea that a matrix, let's look at the pseudo inverse. So the chance that the inverse of this matrix exists is very high. And the inverse, if you think about it, is something related to solving linear equations. You can imagine for n, for just when you just transpose this to 3 or 4 dimensions, the idea that you're so unlucky that even after n equations you can't solve them is very, very low. Okay, so so we spoke a little bit about that. That is, we look and then return x pseudo inverse times y. And classification can also be thought of linear regression, because classification is either 1 or 0, which is also a real valued number, and you can also use the sign. And so, okay, non-linear transformation. So now let's say this is the input data, and now ideally this is the plane that separates, but this is not linear. So the idea here is you can transpose the input data into a different differences, apply some function, and you can still use linear linear regression or classification for that. In this case, what you can do is if you transpose x1 x2 to x1 squares x2 squares, where x1 and x2 are the distance from the origin, consider this 0 0 to be the origin. What you'll notice is that these points gets clustered on the bottom left, and all these go on the bottom right, and now you can see a clear separation. And once this is the case, we'll see how we can actually deal with this in the next set of slides. Okay, so let's look at this. This is a continuation of the lecture. Okay, so once again here, once you have this is what we're talking about. You can separate this, and if you take an inverse, you can actually get back this. But the idea still here is you don't have to worry about taking an inverse. Whenever you see a point, whenever you see a point that you have not seen in this, once you do the classification, once you see a new point, you can just apply the transformation function to it and try to find out where does it land here, and then return the answer. So this particular slide just talks in details about that. Now let's look at error measure. So we know about this. This is the probability of distribution of x. So it's what we are just assume some generic probability distribution that helps Hoeffding's inequality. Conceptually, I think about it as the input data is distributed in some range. You want to make sure that the range in which the input data is distributed is the same, that there is same as the sample data as well and your test data as well. Otherwise, whatever you're doing doesn't make sense. So now error measures, what does h approximately equal to? The hypothesis approximately equal to f mean. There is some error measure. It can be Gaussian, it can be binary error, that either classification, whether it's equal to or whether it's not. And this is the in-sample error. Once again, there are different functions for the same. You can define okay, so now this is where you kind of approximate that gx is approximately equal to fx. Gx is the final hypothesis. And how do you choose the error measure here? The professor is basically talking about that, okay, there is some precision in recall, false positive and false negative, and it really depends. The values of the error measure you put depends on the actual business case. So in this case, for supermarkets, okay, you want to make sure that somebody, if somebody is acceptable, is the correct person, don't throw him out. Okay, so this is very bad. And if somebody is actually not allowed and you still accept him, it's okay. it's not very bad, so maybe give him a lower error value here. But in case of some very secure application, if somebody is not, F is the true and H is the hypothesis. If F is not acceptable, but you actually allow him, that is a very, very bad thing to do. So it's a very high error, you penalize it very heavily. So once again, the take-home lesson, the error measure should be specified, but it is there. If it is not, you can then consider plausible measures that, okay, consider that there is some Gaussian distribution in the noise, and we'll talk about noise and squared error, or it can be some sort of, other measure. So this is where the error measure comes into picture, that there is always some error in Gx, so it's approximately equal to Fx. That's where you bring in the error measure. Now let's look at noise. Now ideally y should be a function. It is a function, but then for the same x you can have different y's. For example, you can imagine for the same kind of a credit worthy applicant, you might sometimes approve him or sometimes not approve it. Like that might be the data that you are learning with. So it's noisy. And hence you want to distribute, instead of y is equal to fx, you actually say what is the probability of y given x. So it can be, let's say you reject him with 0.1 and accept him with 0.9. Now the joint probability distribution is px in px and give py given x, which is also called as pxy, x comma y. So the probability of both x and y happening. And now once again, instead of a deterministic target, you have some noise which is y minus fx. That's the noise factor of the situation, and this is where you're kind of bringing in the noise. Now what you can do is you eventually end up combining these two and just write pxy. Okay, important thing to realize is that this is what we are really trying to learn, py given x. This is just something that's given, and we just merge it for the sake of simplicity and mathematical convenience and say p x comma y. Given all this, the next lectures are all going to be about theory. So we know that E out should approximately equal to be E in, but then that is G is approximately equal to F. But what we really want is that E out should be equal to 0. There should be no error. Okay. Now how do you deal with that? Now if you combine these two, what it means is that E out approximately equal to E in, and E in should be approximately equal to 0. And now this given Hufting's, you have to figure out that, okay, what is the bound that this, what is the threshold that you would accept for this to be equal to 0, and we'll see that instead of finite m, how can we scale it to an infinite m, that is an infinite set of hypotheses. And we look at, okay, that given the error, the in-sample error probably reduces as you increase the model complexity or the dimension. But in this case, as you can imagine, that at some point of time you're no longer learning but memorizing. Thus the out of sample error initially reduces, but after a while it starts to increase, because now you have basically memorized your input space and you're no longer learning a lot. So that's kind of the idea. So okay, so that's those are the things we are going to look at in the next lectures. Thanks.